This video is for class 9 physics and we are doing Archimedes principle in this video. So from our previous knowledge of upthrust and that upthrust is equal to the weight of the liquid displaced, we can understand Archimedes principle also. So when a body is immersed in a liquid, it occupies the space which was earlier occupied by the liquid. That is, it displaces the liquid. The volume of the liquid displaced by the body should be equal to the volume of the submerged part of the body. So the body experiences an upthrust equal to the weight of the liquid displaced by it. Okay, we have understood till here in our previous video. So let me try to make you understand again. Let us consider one container. This container has liquid. Suppose we immerse an object, so partially, in the liquid. What we will observe is, we shall observe that the liquid gets displaced. This is the new displaced liquid, right? By how much? By what volume? The volume of the displaced liquid, this here, must be equal to the volume of this object, right? Now, because of which this object experiences upthrust, Fb, right? And this upthrust must be equal to the weight of the liquid displaced, right? Okay, so this is what we have studied in our previous videos also. I hope you understood the first paragraph. Now let us go back to the book. It is the upthrust due to which a body immersed in a liquid appears to be of weight less than its real weight. That is also known as apparent weight. This thing also we have done. The apparent loss in weight is equal to the upthrust on the body. This is called Archimedes principle. Thus, Archimedes principle states that when a body is immersed partially or completely in a liquid, it experiences an upward force, that is upthrust, and which should be equal to the weight of the liquid displaced by that object. Okay, I hope you have understood Archimedes principle. Actually, it is the combination of these two parts that when a body is immersed partially or completely in a liquid, it experiences an upthrust. We have understood this, right? Whose value must be equal to, that means which is equal to the weight of the liquid displaced. So it contains two parts, right? So when we combine these two parts, which you already know actually, is known as Archimedes principle. Now this principle applies not only to the liquids, but it applies equally well to gases also. Experimental verification of Archimedes principle. Archimedes principle can be verified by either of the following experiments. Experiment 1. Take two cylinders A and B of the same volume. The cylinder A is solid and the cylinder B is hollow. Suspend the two cylinders from the left arm of physical balance, keeping the solid cylinder A below the hollow cylinder. Then balance the beam by keeping the weights on the right arm of the balance. In this situation, both cylinders A and B are in air. This particular figure is not shown, right? Under this condition, what happens here? Suppose we are putting some weights on the other side of the pan, right, of the beam balance, then this will get balanced, horizontally balanced, right? The figure will be somewhat like this, which is not needed actually. So if we have cylinder B and probably cylinder A here, and on the other side if I have a hook and I have a weight there, now this will get balanced, right, in air, first in air, right? But suppose I change the scenario. The scenario here, the solid cylinder A is now completely immersed in water contained in a beaker D. placed on a bench. See, as shown in the figure. Now this situation occurs, right? Now under this situation, what happens is A will be feeling upthrust, because of which the beam balance left arm will slightly rise, because on the other side there is weight. Now taking care that the cylinder A does not touch the sides and the bottoms of the beaker, it is observed that the solid cylinder A loses weight, that is the left arm of the balance rises up. Obviously the loss in weight is due to the upthrust of water on the cylinder A. Now how much should be that upthrust? Now pour water gently in the hollow cylinder B till it is completely filled. It is observed that the beam balances again, that means it will come back to its original position. When it was immersed in water, the cylinder A, then the balance rises up. But after you pour water here, what happens? The balance will regain back its original position, right? So this proves that, okay, the upthrust, whatever it was acting on the cylinder A, must be equal to the weight of the water displaced by it. Thus it is clear that the buoyant force acting on a solid cylinder A is equal to the weight of the water filled in the hollow cylinder B. Since the cylinders A and B both have equal volume, so the weight of the water in the hollow cylinder B is just equal to the weight of the water displaced by the cylinder A. Hence, the buoyant force acting on the cylinder A is equal to the weight of the water displaced by it. Thus, it verifies the Archimedes principle. Okay, coming to the second experiment. Take a solid, say a metallic piece, suspend it from a thin thread from the hook of a spring balance, as shown in the figure 5.6a. Now here what happens is, here you can see a spring balance is holding a solid and shows some reading around 300 here, right? Now what happens is, now take a Eureka can. Now Eureka can is this can here, right? Like a kettle, but its sprout is pointing downwards, whereas even in a kettle the sprout will be pointing upwards, right? Now again, if I immerse this particular solid inside the water, okay, contained in a Eureka can, now you can see the reading will change. Why will the reading change? Because the reading has become 200. The reading will change because this particular object will be experiencing upthrust. Now again the question comes, how much upthrust, right? Now immerse the solid gently into the water, the Eureka can. The water displaced by it gets collected in the measuring cylinder. When water stops dripping through the sprout, note the weight of the solid and the volume of water collected in the measuring cylinder. So here in figure 5.6b, you can see here the water is being collected in the measuring cylinder whose volume is 100 milliliter. Right, from this volume we can calculate the weight of the water also. Now in figure 5.6, the solid weighs 300 gram force, right, in air, whereas it is weighing 200 gram force when completely immersed in water. Obviously this loss in weight is because of the upthrust. The volume of the water collected in the measuring cylinder was 100 milliliter, that is 100 centimeter cube, because 1 milliliter is equal to 1 centimeter cube. We have done this in class 8 also. Now here you can see in the figure two different values of spring balance, one 300, the other is 200. Now this loss here is because of the upthrust. Now coming to the calculation part, loss in weight is equal to 300 gram force minus 200 gram force, which is coming up to 100 gram force, right? So this must be your upthrust. Volume of water displaced should be equal to the volume of the solid. That should be also 100 centimeter cube. Since density of water is 1 gram per centimeter cube, so weight of the water displaced is 100 gram force. How will this weight of the water comes? 100 gram force. Okay, it comes from the mass. Mass is equal to density multiplied by volume. Right now, density given to us is 1, whereas volume given to us is 100. So 100 into 1 shall give me 100, right, gram. If I want to convert into weight, right, therefore weight becomes 100 gram force. If I put this F here, it will change into weight. Mass will change into weight. I hope you understood how this 100 gram force comes. Now from this equation 1 and 2, right, weight of the water displaced here is 100 gram force is equal to the loss in weight of the object, right, which is also 100 gram force. Now thus the weight of the water displaced by the solid is equal to the loss in weight of the solid. This verifies Archimedes principle. I hope you understood this Archimedes principle. Thank you so much this much for this video.